Okay, so welcome to lecture 25 of our CS2 classes. And we started off with copula in the 23rd lecture. And okay, so remember, why do we even need something like copula? Because we cannot always measure things as appropriately using the other tools that we have at hand. So let's say Pearson's linear correlation coefficient, it isn't invariant. But then if you take into consideration rank correlations, which is actually invariant, but then it would measure the correlation between all of the data set. And not always you want to have a look at that. Sometimes you only care about these little corners down here and up there. So what you use is, and what you rather need is some kind of tool which will measure the dependence in the tails of the data set that you have at hand, because that is what you care about at this particular moment. So then we had a look at something which will later on help us to build the tool that will help us to do just that, and it is known as probability integral transform. So the very crux of this transformation is just the fact that you can take numbers spanning from 0 to infinity, and you can maintain the dependency structure that you think there is, and you can get numbers in marginal terms. So let's say marginal, when I say in marginal terms, that means the marginal of x or y. So you start off with the marginal of x and the marginal of y, and then you use copula to bind them together to give you an output, something which is the CDF of the joint distribution of x, y. So at the end, what you get is fxy. So you know that your capital F and capital Y also follow uniform distribution. And again, so it satisfies all the properties first of a distribution. And second, we also prove that this probability is just equal to U. So it allows us to deduce that, okay, this f of x is nothing but just a uniform distribution over 0, 1. So once we establish that, we then go on to have a look at how we measure the dependency in details. So again, this is very intuitive. So if you're looking at the upper tail, you care about this right upper corner here. And that is where you look at the chance of these being greater. And again, you don't use this x. What you use is f inverse of u. So we are just using the fact that your u is f of x. F of x's value is this small u, and you inverse it, and then you just substitute it in place of x. And why do we do this? Because it is always easier when we are trying to simulate random numbers that are between 0 and 1. It doesn't lead to much complex things. And then what you can do is, am I audible? I guess I don't know. I can see that I wasn't sharing the screen at least.
Ma'am, only the screen sharing stopped.
Only the screen sharing has stopped. Just give me a minute. Maybe, I don't know what to do now. Oh, I'm back. Yeah. Okay, all right. So, what was I saying? Yeah, so I guess I was explaining upper tail dependence and lower tail dependence. And yeah, so if you're looking at lower tail dependence, we know we care about this square right here. So yeah, we look at x less than or equal to small x and y less than or equal to small x. And again, because we're looking for dependency, we don't look at and. We're looking at given. So what is the chance that you will observe x here, given that you have already observed y here? So that is dependency that we want to measure. And next up, we saw this Sklar's theorem, which, if I can sum it up, is just saying that copula is something which takes values from 0 to 1. So again, if I look at this copula right here, what is it? It has 0 to 1 on x, 0 to 1 on y. So I can maybe say that my copula is nothing but, just something like a multivariate uniform distribution, because we know copula takes values between 0 and 1. So it does satisfy the uniform distribution's property. So its domain is 0, 1. The values that it's going to take will also be between 0, 1. And it's increasing in nature and all those stuff, that all the distribution properties are also satisfied. So we can say that copula is nothing but a multivariate uniform distribution in general. And again, we know that, this here just says that copula is in a way trying to help us to separate the problem of choosing a dependent structure based on the correct marginal behavior that you have. So sometimes you only know the marginal behaviors, and from that you want to figure out the joint behavior of these guys. So generally what happens is you can have something like this. Okay, so what copula does is it takes input something between 0, 1, and I write a 2 here because we're looking at 2 dimensions, and then it will give you an output which will just be one particular CDF, the joint CDF, and it is taking values between 0, 1. And again, so if I'm looking at these guys, we know the actual values that this x and y take is between minus infinity and infinity. And this here, right here, is the CDF that I've plotted. So this represents f of x. I think I should, I don't know, but I haven't, you see, I haven't written here. This is, yeah, so this is f of x here, and this is f of y. So we know what copula takes in is f of x and f of y as the domain, and it gives us output as something between 0, 1, which will be the value of fxy, which is right here. So this fx and this fy are the things that I have plotted here. And yeah, I guess that's it about this thing. And then we looked at the properties that copula follow. And again, like any other CDF, copula also satisfies the increasing property. And it takes only values between 0 and 1, like any other CDF would, and any other probability would. And again, then we had a look at this UI. So I think this might be a bit complicated for people to understand. So what I can maybe do is I can write an example for this guy here. So let's see if I take just the example of 1, u. What does it tell me? So whenever I'm talking about a particular copula, I know I can rewrite it in this manner. Probability that my x less than or equal to x, y less than or equal to y. So that is what I can maybe do here. So what I'm going to do is I have this thing, and I can write this as probability that my x takes a value less than or equal to 1, and my y takes a value less than or equal to u, right? So, okay, again, this is the value of f of x, and this is the value of f of y. So you guys will have to remember that. And now if you have a look, we know let's just assume for simplicity case, independence, then we know that we'll just have probability that x is less than 1 times the probability that y is less than or equal to u, right? And we know that any probability which will be less than or equal to 1, the probability that this, okay, so I should maybe write this f of x, f of u for now. So I know that my f of x will always be less than 1 for sure. So this is just going to be 1 every time. And what is this? The probability that you will observe a f of y less than or equal to u. We just derived it, right? It's u. So if you have a look here, Yeah, this right here I have used again to just tell you guys that the answer is just going to be something like U, right? And now if you see, that is exactly the same thing that I have done here. So because we had only UI and rest of the other guys were 1, you get a UI here. And again, I would say if you look at the independence copula that will that be derived in case of fundamental copulas, what would this guy's value be? 1 times U, right? Which is just U. So it does satisfy the other property as well. But I guess that was just to give, oops. So that was just to give you guys an introduction, I mean, just some nice example to at least, I mean, make sense of something like this. And then we try to derive the lower tail dependence and the upper tail dependence in terms of copulas. So now that we know I can write my copula in such a manner, what I did was, yes, Isha?
Can you just go back to the properties part for a minute?
Yes.
So ma'am, like when we are saying like C x y of f of x and f of y, like what exactly do we mean by that? And if it means only probability x less than equal to x, y than equal to y, so it is like an intersection of the two.
Oh, okay, no. So that is actually a good question. So, okay, remember whenever I'm talking about, let me just go back to this slide maybe. Okay, so what does this slide tell you? This is the joint x comma y, but what I have is x here and y here, right? Then I use the marginal of y and marginal of x to give me something where I get my values for f of x and f of y, which are again between 0, comma 1 and 0, comma 1 respectively. And whenever I'm talking about a copula, what I look at is the joint distribution. So maybe what can help you is to define another random variable, let's say p, which is just equal to x times y. So you want to figure out its CDF. What is the chance that you will observe s less than or equal to x and y less than or equal to y simultaneously? So this is what the copula will measure. But again, this is not what we want. What we want is a lower tail dependence, which has something like this, right? Because we want to have a look at what's the chance of a particular thing happening, given that something related to it has already happened, right? And this is what you get in the numerator here. And then you will use copula to figure out its value, the dependence structure that you want to have a look at. Does this answer your doubt?
But ma'am, then so if we have like c x y u comma v, so that time it's clear that I want like x less than equal to x and y less than equal to y. But then where you have written like c and bracket u1 star ud, like I didn't
Yeah.
understand what those mean exactly.
Oh, okay. Okay. So remember what I have here is just one variable and two variable x and y. So what I'm looking at this here is probably something. So maybe under this C, I'm not gonna write x y. I will write x1, x2, and so on till xd. So I have d random variables here. So this is probably in a multivariate case, and this was in a bivariate case.
Ma'am, but how will the multivariate case even work?
How?
Because like in bivariate we have two axes each for x and y, right?
Yes.
So in case of multivariate, how can we get so many
Okay,
axes?
so actually there are applications. So there are softwares like Sedge that you can use to teach multivariable calculus, and that's a whole another field of mathematics. But again, I mean, just take my word for it as of now because I certainly can't show that. Maybe I could just pull up a Google or something. Let me check. So actually, more accesses can exist. There can exist as many accesses as you want. Because I mean, even for the people who do solve this real world problems, there don't exist two things, right? Every time. So you do have a look at this multivariate case and Yes, let me just check. So you would have like, these weird diagrams and sketches. I don't know why is this not working. So weird. Do you see something here? This looks a bit weird, right? So, I mean, this is the kind of stuff that you will get if you're looking in more dimensions. I think the maximum dimensionality that our human brain can at least draw. Okay, so I think there's really, good connection between these things. So remember, okay, I mean, just look at what we can do as humans, okay? We take a paper which has two axes, x and y, and we can draw something which is 3D on that paper, right? And let us say if you have 1D, you can draw a 2D on 1D, you can draw a 3D on 2D, but you can never draw a 4D on 2D. You can only draw a 4D in 3D. And that is, I mean, there is a, I don't know, it's Lagarde or I'm forgetting the pronunciation and the name as well. There is something in Paris. It's actually a statue, not exactly a statue, but just, a cube, I would say, a 3D cube. So what they have tried to do is they have essentially tried to create 4D. So you can be right there and you can see a 4D cube. I mean, it wouldn't be called a cube anymore because it's cube in a 3D. And when you are looking at it in a 4D, you can only have a look at that 3D cube's shadow on the ground, and that would be your 4D illusion of a cube, I would say. So it's really impossible for even human brain to visualize this in more than 3 dimensions because we can only see x or y and the third axis coming right out of the board, right? And because we live in a 3D world, if by somehow we weren't living in a 3D world but 4D, maybe we could have figured out a way to visualize 4 axes, but we cannot possibly do that. So you will have to trust the mathematics of these people to just take it for granted that yes, this exists. And this would not only hold true in the case of 2, but also in the case of multivariable case. And again, there are proven mathematical techniques that you can use to prove such things as well. So you can use the iteration method sometimes, because if it let's say works for one thing, then it's going to work for the other cases as well. But yeah, I guess there's rigorous mathematical proof that goes behind these even properties of the copula and even the derivation of each copula. So, I mean, if you're really interested into that, I would suggest for you to, take up some higher level math courses. I think there's a good website, MIT Open Courseware, where you get almost everything for free and taught by high world-class professors as well. So I would say, I mean, you should really look into that if you're interested into this. But I really like that you asked this question, Isha.
And ma'am, just one last thing, like for the CXY, you have written it equals to probability x less than equal to x. But here, when you've given the 1 and u example, you've written probability f of x less than equal to 1 and u.
Oh, okay. So wait, I see what's happening. So okay, whenever I'm talking about this guy right here, what I have done is, what do I care about? So remember, I mean, so okay, my x is the random variable here and my y is the random variable here, right? But what is my u and v? These are just the placeholders for this x and y, right? Do you
Yes,
agree?
right.
So
Yeah.
every time I write f of x, what is this? This is the value that this guy takes. But again, remember what is my u and v here? Is it x or is it f of x? It is f of x,
It's
right?
f of x. Yeah.
Yeah, so that is why I take f of x. I mean, my ui is just f of x.
No, ma'am. So on this page only, like along the same line, what you've written beside f x y equal to probability.
Yes.
So that should be f of x less than equal to x, right?
Oh, no, not always. I mean, what do you mean? You mean instead of x here, I should write f of x less than or equal to x? Is that what you mean?
Yes, ma'am, because that's what you've written in the next part, right? Like what you gave right now, the example.
Wait, let me check. Yeah, so I said that I have C1 comma U, and then I wrote f of x here. And okay, so maybe what I just meant was not that, I think. I guess maybe I should just write this again. Okay, let me just write this again. Forget about what I wrote previously. I guess I got carried away. But the actual thing to write would be something like this. So I have x less than or equal to 1, comma y less than or equal to 1. And because these guys are independent, what I can write it as x less than or equal to 1 and y less than or equal to 1, right? Okay, should be u here, right? And this is the probability, and I'm multiplying them together. So this probability that x is less than or equal to 1 is just going to be 1, and the probability that you observe a y less than or equal to u is going to be u itself. And that is how you get your answer as u. But whenever I'm writing c1 comma u, I think, so I mean, copula should always be equal to this. X less than or equal to x and y less than or equal to y.
Yeah, got it, ma'am. Thank you.
Got it? Okay, yeah, I guess that was clear, and thank you very much for pointing that out, Isha. Okay, so now that we have discussed about lower tail dependence, the similar thing you would do for the upper tail dependence as well. And what you will have here is, I mean, you'll have to use some Venn diagram stuff to just figure out what you will write in numerator for this case. Because it's not as easy as writing 1 minus the observation of these both guys being less than their respective values. So you'll have to take into consideration these as well. And luckily, we do know what the values of these and these is. So it is just u and u, and this can be summarized as just copula. So for the upper tail dependence, the coefficient will be something like this. And again, we also try to use a survival copula to write this in another terms. And I guess that is just about it. And we discussed what a survival copula is. So it is a bit like a complement where you are looking at, just not only, I mean, it's just another way to write the same thing that you're looking at. So here, if you're looking at this, you can rewrite it as f, and you can just write a bar over here, which would represent that you aren't looking at f of xy, but I mean, not less than, but greater than sign. And then you go on to derive. Okay, now this is the most interesting part and much more important from the perspective of exams as well. So we have to study various kinds of copula. And the very first kind of copula that we studied was fundamental copulas. And within it, you will have 3 different kinds of fundamental copulas that you can have, depending on the 3 fundamental relationships that you observe within any data set. So the very first is that these data can ideally be independent of each other. I mean, these variables are independent of each other. And if that is the case, as we would have expected, there should be no dependency in the lower tail or in the upper tail. And if you use this copula function, which is just u times v, to substitute in for the value of lower tail dependence and the upper tail dependence, in limits, you do get the answer 0 and 0, which does satisfy the criteria that we set out to look for an independent copula. So yeah, it goes well. And next up, we had a look at the common alternate copula, which is something which will help us to assess whether there is a perfect one-to-one relationship and a positive relationship between the random variables that we're looking at. So we had a look at an example which would just satisfy that relationship. And we tried to derive what kind of a function that our copula must satisfy. And then we said that, okay, I'm now defining my copula for all the common alternate cases as something like this. And remember, this u and v are the values that can only take numbers between 0 and 1. So again, we tried to have a look at it, and we saw that if we try to simulate this random values, let's say if I give you guys a value of u, now, which is A, and if I tell you that the dependency structure here is something like a comonotonic case, where these guys are perfectly positively related to each other, then you can easily say on the basis of these information that I have provided to you that your V will also be A. Because if you have a comonotonic case, I mean, again, because we have 0, 1 and we are looking at the perfect relation, there is a 45-degree angle that this line will create. And there is no deviation and nothing else that's going on. So you would get a perfect mirror image of these axes across this copula that you have. And then we also had a look at the counter monotonic case, wherein we see that there is no dependency. So there's nothing that goes on here and nothing that goes on here. But again, we see that these variables are negatively correlated with each other. So if this is the case, if you have u equals to u, then you will have v equals to 1 minus u. Because I guess it's easier to just see it from here. If you take a value for u as 1, v is 0, right? And if you take corresponding similar case here, you get the value of u0 for v equal to 1. So it's just going to be 1 minus u. And again, remember the dependency here is 0. I mean, not any dependency, but the tail dependency at least is 0. But still, there is a negative correlation between these variables here. And we sort this using an example which will just follow something like negatively correlated random variables. And then we had a look at how to visualize this, and we saw what bound copula has in 3D. And today we are going to have a look at another family of copulas, which is known as explicit copulas. And again, explicit, why? Because I can actually write the formula that these copulas will have in terms of, these will be solvable. So I'm just going to write heading here, explicit copula. Again, there will be various different kinds of explicit copulas that one can see, and one of them is actually Gumbel copula. So Gumbel might ring some bells from what we studied in extreme value theory. That was something like Gumbel type generalized extreme value distribution. And again, we see the Gumbel guy here again. So again, I think I'll tell you the difference between these guys. But yeah, okay, I showed you guys the pictures of these copulas yesterday, right? Of the Gumbel copula, the Clayton copula. Maybe I can pull up the book today. So the thing that you guys studied in extreme value distribution and the Gumbel copula that you will be studying now are not at all related, and they are two separate things, and we'll see. So yeah, so Gumbel copula would look something like this, and if you see, you can actually see that there is not much. Can I see my cursor moving? Yeah, no. Okay. So if you look at this upper tail right here, you see there's not much variation, right? But if you have a look at lower tail, there is so much of variation here. But again, there's not quite a lot. So you would see that, this Gumbel copula is best if you sense that there might be some upper tail dependency within your data. So you would try to use a Gumbel copula. And then there is another kind of copula. We'll have a look at these derivations as well about how you derive these formulas. But then I'm just going to show you guys graphs first. And then if you're looking at Clayton copula, this is very much evident here, right? I mean, there's nothing that you can say of these guys, but let's say if you're looking at the lower tail dependency, Clayton copula is what you've got to use. And then if you're having a look at Frank copula, it's just all over the place. So you cannot really measure any kind of dependency in the tails, at least using the Frank copula. So these are three different kinds of copulas that we are going to cover in explicit copulas, which also form a part of the Archimedean family that we will study about. So I showed you guys how these copulas are, And even before we write the formula of this copula, I just want you guys to derive a copula by yourself. So we'll try to build a copula right now. And let's see how do we do that. So I guess instead of writing explicit copula, I'm just gonna write something. Okay, so let us start with what we had initially. Okay, I have f of x comma y, which I think is, I mean, of course, is equal to this thing, right? Y less than or equal to small y. So now what I do is, using this joint, I define marginal distributions. So what I'm going to do is, I'm going to define marginal distributions. So remember what I'm doing is, remember those 4 diagrams that I drew? I started off with f of xy, and now I'm defining my marginal distributions. So I'm going from this graph to that graph. And first, let us do it for f of x. And again, remember this is for x, capital X random variable. So what I can do is, I can sum this guy across all the values of y that I have. And let us assume that it goes on till infinity. So you'll have this, and you can again rewrite this as just something like this. And then you can maybe have a look at the same case for y guy, where again I'm assuming that my x goes on till infinity, and this can just be again written as probability that my y takes a value less than or equal to small y, right? And now I will again, so what I did next was I had my CDFs, then I defined those CDFs in terms of their distribution, which I knew was just uniform, right? So now I'm going to use probability integral transform to define some uniform variates. Okay, and what I will just write here is that my u is f of x and my v is f of y. So nothing new up until now, but now what I'm going to do is, let us try to consider what copula is. So we want to build a copula using all the information that we have. Okay, so now I'm going to write a C, U, comma, V. And what do we know about this right here? That I can rewrite this C of U, comma, V as probability that my U random variable will take a value less than this U guy, comma, my V random variable taking a value less than this V guy right here. So again, I can write less than or equal to, doesn't make much difference because we're looking at continuous cases. And again, remember, if these marginals, f of x and f of y are continuous, then we would have a unique copula for each of these cases. So, okay, now that we know this, what I'm going to do is I'm just going to substitute instead of u and instead of v, this f of x and this f of y. So you always need to compare apples to apples and oranges to oranges, as we say, right? If you're writing f of x less than or equal to u, that makes sense. But if you write f of x less than or equal to x, does not make sense. So again, if you're writing this in terms of small u and v, you take f of x. And if you're writing this in terms of x and y, you take capital X and capital Y here. So now that we are writing it in terms of u, I'm going to replace this with f of x less than or equal to u, comma, f of y less than or equal to v. All right. But again, what do we want at the end? We want a formula for this copula guy. And what do we know about the domain of copula? That we only know the values of u and v. Let us say you have only simulated up until now the values for u and v. So you want to have at the end something in terms of u and v, right? And the function that you know about. So this f and f, you're fine with those as well. So now what I can do next is, again, do the usual inverse trick that I do. So what I'm going to write is, apply f inverse on both these sides. And this will give me something like this. So here I would get y less than or equal to f inverse of v. Okay. And now what I can do is, so this is probability that I will observe x less than or equal to f inverse of u, comma, y less than or equal to f inverse of v. And what is this? So if I have probability x less than or equal to something, comma, y less than or equal to something, I can write it as f of x, comma, y, right? So I'm going to use this fact here to write this thing as f of, and instead of x and y, now I'm going to write these. So what I will have is f inverse of u, and again remember this is with respect to x, comma, f inverse with respect to y, v. So you see what do we have now? And this is your formula, basic formula for copula, I would say. So what we have derived is C u comma v, right? So now this is what we'll be using to build these explicit copulas. And again, why do we even call them explicit copulas? Because we can derive their formulas. And this is how you are going to build a copula. So this is just basically, a recipe for you to build a copula, and again, not in multivariate cases, but only in bivariate cases. So here we are building a copula. So now we can have a look at this explicit copulas, and we'll try to see if there is some connection between the way we just build a copula, because now that we have done this, we know that every copula's function that we see, it should look something like this. So there will be one particular value for f, and again, you would get some inverses here. So let us have a look at Gumbel copula, I would say first. And its formula, I'm just going to copy it from the book, even I don't remember it. Gumbel was actually, a very interesting guy. So, I mean, first of all, he was a very politically active personality, and his story is actually a bit weird, I would say. I mean, he was a German mathematician, and again, because he was very politically active, he used to write against Nazis at that time, and because of which he was thrown out of his country at some point, and he fled over to France, and then he started teaching at a college over there in Paris when one of his friends was accused of murder. And in trying to prove to the judge that he was ignoring a certain factor in accusing his friend guilty and trying to prove his friend innocent, he snowballed into discovering copulas, where he was the one who actually coined this term as well. So he was actually he started to work along with Tippett and Fisher, and then they also published a book, and now we have this little nice Gumbel copula in his honor, I would say. And it's really, nice to see these people who weren't, at best of their circumstances and still giving us things that we are very glad to have. Is this so? Let me just write. I have explicit copula. Okay, so if I'm looking at Gumbel copula, its formula is something like this. So again, you will have u comma v, and you have e raised to minus of this. Can go on here. Not really great at copying. Alpha plus minus of log of v alpha, and this everything raised to 1 over alpha. Okay, so now can you guys tell me one difference between this Gumbel copula and the Gumbel extreme value type distribution that you guys saw? One basic difference that you guys see. Anyone? What difference do you guys see? Anyone? The basic difference that you see in this Gumbel copula that I have written and the Gumbel type GEV distributions formula that we studied back. Come on, I'll wait. So I'll give you guys time to think about that. Until then, we can actually, sit and derive this till dependence for this Gumbel type copula. Okay, so now I'm going to assume. So what I want to figure out is just for u comma u. So remember for Gumbel, we're doing this for Gumbel guy. So we have e raised to minus of log of minus of log of u plus minus of log of u again, and everything raised to 1 upon alpha or e raised to 1 alpha alpha. So now if we have u comma u, what should I be writing next? Anyone? I can just sum this across, and what I will instead have is 2 times minus of log of u raised to alpha, and this everything raised to 1 upon alpha. So this alpha and that alpha would just cancel each other out. Do you guys agree with what I have just done?
Yes, ma'am.
What about others? So I actually cannot cancel this 1 upon alpha and alpha directly until and unless I write a 2 raised to 1 upon alpha here. Because you see there's a square bracket here, and we not only have 1 raised to alpha on this log u, we also have 1 raised to alpha on this 2. So I'm going to keep this, and for this guy, I'm just going to write it as minus ln u. And now I can remove these minus. So what I get here is e raised to log of u times 2 raised to 1 upon alpha. And again, I can take this coefficient in here as a power. So what I'll get is e raised to ln of u raised to 2 raised to 1 upon alpha. And we know anti-logarithm and logarithm will just cancel each other out. So what you're left with is something like this. Do you guys agree with this? Right? So the value of my Gumbel copula in the case where my u is equal to v, so I get this. And again, this is something where I'm in a way, so now I'll just try to figure out my lower till dependence and the coefficient of upper till dependence. So let us try to figure out the lower till dependence. Lambda L. So what was the formula? I guess it was just C of u comma u upon u, right? But again, tell me one thing. What do you guys think is going to happen if I try to figure out my lower till dependence? Forgot to let that remains. Anyone? What would you expect my coefficient to look like? So again, remember I'm looking at Gumbel, and now I want to figure out its lower till dependency. What would you guys guess from what you know about the Gumbel up until now?
Will it be close to 0?
Yes, exactly. So it's going to be close to 0, right? Because what did we see? That there is no tail dependency in the Gumbel copula. So again, if you try to derive this, what you're going to get is something like this. So I was using blue. Yeah. So you will just have limit u goes to 0 minus. But now if you replace this copula, what you'll have is u raised to something upon u. And now if you substitute this 0 in the numerator and denominator, you get something which is 0 upon 0, right? So this is indeterminate. You do not know its value. So you will try to use L'Hopital rule. And what you will do is you will differentiate this numerator and you will differentiate this denominator. So in the denominator, you will get a 1, and in the numerator, you will get again something, but it will be multiplied to u to the power something. So if my u is going to 0, this is just going to go to 0 at the end, right? And we can see this L'Hopital, which I just explained in a hurry, I guess, clearly when I'm trying to do the upper tilde dependency. So can you remind me what is the formula for my upper tilde dependencies coefficient? What are my limits on? So my u approached 1 from below, right? And now if you try to substitute
and for the lower, like the lower tail one, it is u tends to 0 plus, right? That's what.
Oh yeah. Yes. Thank you very much. Good observation. Yeah, it should be. Oh yeah, plus and minus here. Yes. Good. Okay. So now that we are here, what will we do? Let's just substitute the copula first. So we are looking at 1 minus 2u plus, and instead of copula, I'm just going to write this thing here. Plus u raised to 2 raised to 1 upon alpha upon 1 minus u. And now again, if you try to substitute in 1 here, you get a 0 in the denominator because 1 minus 1 is 0. And if you try to do the same thing here, you get a 1 minus 2 plus 1 because 1 raised to anything is going to be 1, irrespective of whatever value your alpha takes. So this is again something like 0 upon 0, and this is indeterminate. So what you do is you use L'Hopital rule, you just remove the s and you get spelling. So you are looking at L'Hopital rule where you differentiate this numerator separately and you differentiate this denominator separately. And now what you will have is limit u going to 1 minus. Also, one's differentiation is just going to be 0. And here you will have minus 2. We'll do that thing later. And I have a minus 1 in the denominator. So now I'll have to differentiate this guy. So we'll just use chain rule, and this power will come in the downstairs first, and you're going to have u raised to 2 raised to 1 upon alpha minus 1, and this is in power of u now, right? And now if you try to substitute 1, what do you get? So this will just be 2, and again if you try to substitute 1 in here, what will you have? 1 raised to anything is again going to be just 1. So you're left with this thing here. And remember, if you would have again, if let's say after differentiating it once, you would again get 0 upon 0, then you would try differentiating it again. And that is what your L'Hopital rule states. So until and unless you get to a point where these aren't 0 upon 0 or in any other indeterminate manner, you can still continue to differentiate. But again, this is not going to work every time. But yes, it does work here. So kind of makes our life easier. So you see what's happening here is that this is not actually 0. But again, we know that this depends on what? This depends on the one parameter that you have here, alpha. So have you guys figured out the difference between the Gumbel copula and Gumbel type GEV up until now? Anyone? I guess I just told you guys the answer as well. So in Gumbel type GEV distribution, the number of parameters you had were 3, right? Alpha, beta, and gamma. Here you only have 1 parameter. So for copulas, you only have 1 parameter. So again, in paper, if you see Gumbel 2, I mean, I think there will of course be words like copula and extreme values. So, but yeah, again, just to, not get confused, just remember in copula, you only have 1 parameter, that is alpha here. And that is what will dictate how this Gumbel copula behaves again. So let us say if your value of alpha increases, because this is 2 raised to 1 upon alpha, if your value of alpha increases, okay, let me just, maybe I can write it here. So if my value of alpha increases, I know my 1 upon alpha decreases, right? And if my 1 upon alpha decreases, I know my 2 raised to 1 upon alpha also decreases. And if this decreases, I know that my minus of 2 raised to 1 upon alpha will increase, right? And which is why, as in when alpha increases, so would the upper tail dependence increase. So the more value of alpha you observe, the more likely it is, I mean, not more likely, but the more degree of upper tail dependence you will observe in your Gumbel copula, which is here. Okay, so the more value of alpha you have, the more strict this will be. And the lesser value of alpha you have, it's gonna go white. Actually, where is that? Yeah. So this is a bit about Gumbel copula. And now in the similar manner, what you can do is you can just try to derive the tail coefficients for the other kinds of copula as well, just so that if you, I guess, want to practice, I guess in the chapter end questions, they have asked you guys to do the same. So I would say that would be a very good practice. And often, so in the last year's paper, which was in 2020, in the IFOA paper, they really asked these kind of questions for copula, and there was a question in the mock as well, and I'll be uploading those soon, I guess. Okay, so now we'll have a look at Clayton copula, which is another kind of explicit copula, which is N, that you have a perfect function for. So if I'm going to write this value of copula for two different bivariate case, this would just be u raised to minus alpha plus v raised to minus alpha. So again, you see there's only one parameter, alpha, and that is going to be common with each of these explicit distributions that we study. And remember how the Clayton copula look like? It measures the lower tail dependence, right? So you're going to have lower tail dependence that you can measure using Clayton copula. Yeah, and I guess the next kind is Frank copula, which won't really allow you to measure things clearly. Its formula does look monstrous to me. It's minus 1 upon alpha. I think anything related to Frank's derivation is surely not going to come up. It's just very difficult to write in using a pen, so you can only consider writing it in Word. Yeah, this is how your Frank copula looks like. Looks like that in terms of math, but when you're looking at it in terms of this diagram, there's really no tail dependence going on anywhere. So again, you can't really say that if your u or v is going to be higher, then whether your other respective variable is going to be higher or not. So again, these are three basic types of explicit copulas that we studied, and there is something common in between all of these copulas. Okay, so we looked at Clayton copula and we had a look at Gumbel copula as well. So I guess it's much more evident in Gumbel than in Clayton and Frank that we actually used something like this, right? So when I was trying to define any general copula, so this is, let's say, my general formula for explicit copula, what do I have? I have a f here, and then I have f inverse in there, and I have f inverse in here. So if you try to have a look at this guy, we see that E and log are inverse of each other. So where did the equality go? So if I'm looking at, let's say, if I, let's say, try to figure out what exactly my f is, I can actually do that in the case of Gumbel copula. So this way of writing distributions is actually, so what happens is in your book, they have given you directly this in terms of something else. So what they have given you is, so again, we know that whatever we have outside, we have its inverse inside, right? So now I'm going to define something pink. So what I will have here is, I'm going to write the formula that you guys have in the books for Archimedean copulas. So they say that this is another kind of copula that you can have. and which also forms a part of explicit copulas, and Gumbel, Clayton, and Frank copulas are derived from this again. So I'm going to define, let's say, Archimedean copula. And this is again going to just, give me a general function. And again, I'm looking at only two variables. So this is a bivariate case where you will have something like this. So remember, I could write this as anything else. This is just a way to denote a function and just trying to use a Greek letter, which is there in your books, plus this v. And this function right here is actually known as generator function. And why do we call it a generator function? Would anyone want to guess? Why do we call this a generator function? Because it helps you to generate a copula, right? So, and the only fact that you need to know is this particular function, you can generate a copula, because if you know this, you can again figure out its inverse as well. So this is in a way, just rewriting what we derived earlier. So F inverse, you have this guy, and this guy's inverse would be this guy right here, right? Does this make sense to everyone? Yes, Anu? Are you guys there?
Yes, ma'am.
Yes, ma'am.
Oh, okay. Yeah, thank you very much. So again, sometimes what happens is these inverses may not exist. So that is the case why, that is the reason why in the books they have mentioned pseudo inverse function, right? It's not exactly inverse. So whenever I'm talking about a pseudo inverse function, it is just another way of defining an inverse function such that it has a value everywhere. So for the cases where we won't have a particular value for pseudo, for an inverse function, we can just say that it's going to be 0. And when you use this trick, we define the actual inverse, the original inverse that we started off with, as something which is a pseudo inverse. So I guess that's all you need to know about the pseudo inverse. But again, now let us try to derive this Gumbel copula using what we have here. So if I tell you guys to guess what will be my generator function here, how would you guess it? So maybe I can write it again here. So what I have is this thing inverse, this thing u, plus this thing v, right? This is what I have as my generator function. So what I want to know is, what is this for Gumbel copula? Would anyone want to guess? So remember, what I have to do is, I have to look for this function within this formula right here. Are you guys trying this in your books using pen and paper? I hope so.
Ma'am, there was a network error on my end. Could you just repeat what you have to do?
Oh, okay. All right. No worries. So what you guys have to do is, so did you understand the way I wrote this generator function? Were you there?
No, ma'am.
No, okay. So what I did was I just explained something about Archimedean copula, which is just using this, the way we derived the copula here. So we have F here and F inverse in there. So similarly, you just, and they are just rewriting it in terms of different Greek letters, but you have something here and it's inverse in here, right? So you have an inverse here and just its inverse, which is just the function itself as the domain. And this we call as generator function. And again, remember, this is not an inverse. This is in technically correct terms, this is actually a pseudo inverse. So should maybe just write it here. This is actually a pseudo inverse. So whenever I'm talking about pseudo inverse, I not only look at the actual inverse, but I take a value, but my pseudo inverse will take a value of 0. So this guy will take a value of 0 if my inverse does not exist. Because not all functions are invertible, right? And now what I want you guys is, I want you guys to figure out what this generator function will be for this guy right here. So you want to compare this function right here with this expression that I have written over here, and tell me what will be my general value of this psi x. Anyone? Are you guys trying? Can I at least have a yes or no so that I know which one of you is trying?
Ma'am, will it be minus ln mu raised to alpha?
Yeah, it will be right. So if you just try to compare, okay, what about others? Do you guys see what's happening? So Sauri, can you explain to these guys why will it be what he just said?
Ma'am, like you said, the generator function, the inverse should be like we will get mu, right?
Yeah.
For the generator function. So if we do e raised to minus and like we take it inside, ln mu will be. So I just figured out that it will be minus ln mu. But
yeah.
It
So
will
maybe
be the whole, yeah.
Okay, so I guess what she's trying to say is we have this psi of x, so it's just going to be minus log of x and everything raised to alpha. And let's say if we do this, what will we have? So we see that we have this inverse and we have this plus this, right? And if we look at this, I see that there is this guy plus this guy. So maybe I mean, whenever I'm trying, my first guess would always be, okay, let me consider this whole thing as my psi of u. So if you do that, then now you would also want to know what is your inverse, right? So now you try to take inverse of psi of x. And for that, you equate it to, let's say, something p. Okay, and now that you have a p, what will you do? You want to write this x in terms of psi inverse. So what is my psi of x? It is minus of log of x raised to alpha equals to p, right? So what will I do? I will just rearrange everything in terms of this x, because whatever my x will be is going to be psi inverse of p, right? So my psi inverse function will just be dictated by what equates my x in this. So if I try to solve for this minus, I will just take it over there. So I have, let's say, log x equals to minus of p, and that will be raised to 1 upon alpha. And then this will just be x equal to e raised to minus of p raised to 1 upon alpha, right? of whatever value that your P will take. So now you know that this thing right here is what is your psi inverse of P, right? So now if you were to define this psi inverse function, what do you have? For psi inverse of x, you have that it's going to be e raised to minus, instead of P, I will write a x raised to 1 upon alpha, right? So this is what you have now derived. And if you try to substitute these again back here, you know what is your domain psi of u plus psi of v, which is exactly this. And instead of x, you will have all of this raised to 1 upon alpha precisely, and you have a minus here. Yes, we got that. And E. So voila, what do we have? We have this psi of u and psi of v values separately. And so basically we know our generator function and its pseudo inverse as well for the Gumbel-Coppola case, at least. Does this make sense to everyone? Okay, was that clear to everyone?
Yes, ma'am.
All right. So now I guess in this, you can just have a look at how we define pseudo inverse functions. So yes, this is where they explain what the generator function will be and its inverse for this Gumbel guy. But remember, whenever we are trying to define pseudo inverse function, sometimes for some values of x, so let us say this square root of x, which is the inverse of x squared, only exists for a positive number of x. If we don't take those complex numbers into account, this would only have a particular number as integer for real values of numbers, so which are positive. So for every negative x, you will have something else. So what happens is sometimes you want to define this inverse in such a manner that it takes the value of original inverse if your x is between 0 and psi of 0. So psi of 0 is, let's say, the minimum value, and then you have a 0 here for these guys. So again, this is nothing but, so this is just like an ordinary inverse function. But again, for all those values where inverse does not exist, you just assign it a value of 0. That's it, nothing much. So I guess that is all you have. And again, here they have defined the same family of copulas, the same Archimedean copula in terms of the dimensional case. So it would still have an inverse here, and instead of summing up 2, we will be summing up b psi ui's. So that's the only difference. And here in these two lines, they actually summarize what we saw in the graph, right? So again, we try to check whether this is indeed a valid copula or not. So we know that this psi of ui. So first of all, this ui is the domain which takes values between 0 and 1. So I'm giving in a value which is between 0 and 1 to my computer. And then I substitute in this 0, 1 value within my generator function. And it will output me some value between, let's say, minus infinity to infinity, or let's say 0 to infinity if we define it for only positive subset. So we'll say that my generator function maps values from 0 to 1 to 0 to infinity. So it takes values u, v, and such which are between 0 and 1, and it gives me values which can lie between anywhere 0, infinity, right? And now if I do psi inverse, it again gives me back something which is between 0, 1. So if and only if that is the case, this will be a valid copula, right? Because we know one of the properties for a copula to exist in a well-defined manner is that it should lie between 0, 1. So again, that, and then for it to satisfy other properties, you also need this generator function to be a continuous, strictly decreasing convex function with its value at 0 when this is 1. So we'll have a look at how it looks like. I guess they have given you numbers here. Wait, what is it that we have here? Yeah, this I guess we've already discussed. Yeah, so again, for it to be a valid probability, it should be between 0 and 1. So yeah, this is how the Gumbel's case would look like. So we are plotting the generator function. So it is decreasing, right? And it is continuous, checked. And now it is also convex. So if it would have been concave, it would look something like that. So it is convex to the origin, to be precise. And that is what we want our generator function to be. But again, we also want that, whenever my generator function, there was one more property, right? That whenever it takes a value of 1, it should be 0. So now what happens if you try to substitute a value of 1 here? So if instead of t, if you substitute 1 here, what do you know about log of 1? Log of 1 is always 0, right? So my log looks something like this, where it takes a value of 0 every time for 1. And again, now depending on your alpha value, you will plot this minus log of t alpha, and you will get something like this. So what they have plotted here is for alpha equals to 5. And that is how your Gumbel-Copulas generator function would look like. So, okay, once you know this generator function, you can actually figure out the formula for copula, right? Just the way we did it. So what we did was, we tried to figure out the generator function using the formula of copula that we knew for Gumbel. But that wouldn't be the case every time when you do this thing in practical. You would have the generator function, and you will use that generator function to figure out a formula for the copula that you need. And again, that will be dictated by the kind of dependency that you expect, or the theories in finance or in economics dictate there is amongst these variables that you're looking at. So again, I guess, yeah, here they have just, they have actually explained how do we derive this inverse generator function. So yeah, I guess that's it. And what are they doing here? Oh, so here they're just trying to confirm whether this generator function is a valid one or not. So yeah, if you substitute t equals to 0, you do get infinity. If you substitute 1, you do get 0, which is good. And in this range, it takes increasingly negative values. I mean, we just saw its graph, right? So yeah, it does satisfy all of these properties. And these are the generator functions for copula, for Clayton copula, and for Frank copula. And again, please mind the values of alpha that these guys are valid on. So this is taking values from -1 to infinity, and this guy goes from -infinity to infinity. So I would say that's it. And again, I mean, whenever we're looking at independence copula, they're saying that its generator function is going to be minus log of t. So these are just a couple of generator functions for different kinds of copula. And I guess you guys, I mean, so they have actually derived as well. I mean, they have asked us to show whether this generator function indeed generates the independence copula or not. So, I mean, once you know the generator function, what's left for you is to just first figure out its inverse. So you equate this to some x, and then you figure out its value in terms of t. So t is equals to this inverse of x, which is just going to be e raised to minus x. So if I have this t equal to x, which is equal to minus log of t, what will I have? I will just, basically minus will get transferred here. I'll have log of t here. And this will just give me something that my t is equals to e raised to minus x, which you have right here. And what was your t? So again, when you defined this thing, you can also say that your t is equals to this guy inverse of x. So this t will be equal to psi inverse of x, which is just e raised to minus x. And once you know this, you can try to generate the copula. So remember, what do we have to do? We have to take its inverse and then just add this for u and v. And what you get is, so minus log of u minus log of e. I mean, you can, okay, to get to this, you have various methods. you can take minus common and write it as log of u plus log of v, and addition will of course give you log of uv, and this will just be minus. So yeah, I guess, did I mistake? No. So you will have e raised to minus of this minus log of u, right? So I guess that's it. Otherwise, you can also take this as minus log of u, and because you have minus v, this would go in there. But again, if you have this minus here, you can, oh no, don't go down that road, I guess. I don't know what was I doing here. But yeah, you can actually look at this minus log of u minus log of v as well. But I guess the easiest way is just to take this minus as common, and you get this answer, and you arrive at u times v, which is indeed the way we defined the inverse, sorry, the way we defined our independence copula, right? And again, you need to check the validity of generator function. So at 1, yes, log of 1 takes a value of 0, and at 0, yes, it tends to infinity. So I guess, and yes, I mean, in the range of t and 1, because my log of t is an increasing function, my minus log of t is going to be a decreasing function. So yeah, that's all you have here. Any doubts with this question, anyone? So actually, this is the kind of question that you will have to answer in exams as well. So remember this copula chapter isn't really that difficult. It is straightforward. Although while I was reading the commentary for the previous, the last time I taught this class, I don't know why students still found those easy questions from the exam difficult to solve during the exam time. So I would just say that, practice this and try to be aware of what are the things that you are doing, because I know there are so many things going on that it might be even difficult to keep track of. But again, I guess if you just chop it down that, okay, first we try to, just have, you guys do have summary of these lectures and what are we covering in each topic as well. So try to have, an outline of the chapters. Okay, first we studied this, then we studied this, and then we studied different types of copulas, and then we studied more types under those types of copulas, and we studied the bivariate case, and so on and forth. So I guess this was it about this copula. Okay, yeah, now these are interesting copulas. So the third type of copulas that we have are known as implicit copulas. And again, we call them implicit because one, you cannot really, write a closed form solution for this copula. So you won't really have an expression laid out at least in terms of log and e, the way we had it in terms of Gumbel, Clayton, or Frank. But we are just going to use the generator function, and not exactly the generator function, but the thing that we derived, previously. So the F and F inverse. So if you have a look at the Gaussian copula formula that they have mentioned here, I said copula, right? Yeah. So Gaussian copula, if you have a look at this formula here, and that's just the formula for it. And to look at the kind of dependency it will measure. So again, here what they have done is they have plotted this bivariate Gaussian. So again, bivariate why? Because we are looking at two axes. Oh, it's gone again. Can you guys Hello, I guess I'm back now. This is so irritating. Okay, yeah. So what I was talking about is this Gaussian copula. So if you have a look, it doesn't quite well measure the upper tail dependency, neither it measures quite well the lower tail dependency, right? So I don't know how many of you guys read the article that I posted, but this is what the article says. So in actual, what happened was these finance guys, they used Gaussian copula to price the securities. And by doing that, they actually underestimated the dependency that there was. So if you have a look at Gaussian copula, you see that if this guy takes a value which is much higher, give me a minute. Okay, so what I was saying is, now that if we have a look at u, let's say, which takes a value 1, and we want to see that given that my u is taking a value 1, what is the chance that my v will also be 1, right? So you don't necessarily know because you have these many into consideration, and it could either be, it could be anywhere here, right? And you can't necessarily see that it's going to be in the upper tail itself. So if instead you were looking at a Gumbel type copula, which does measure the upper tail dependency, you would have guessed that yes, if there is a u which is going to take a higher value, there will be a v which will take a higher value. But so I guess that is the reason why if one has to, look at the data about recession or the depression, and let's say if you're looking at the credit losses, where your dependency among the credits will increase, and thus you will experience a higher loss, you want to look at Gumbel type copula so that you do take into account anything in the upper tail right there. So the extreme values, yes, they do matter a lot. And remember here, this graph is not how Gaussian copula will look like always. This is the Gaussian copula for its parameter rho taking a value of 0.85. And again, can someone tell me how would this Gaussian copula look like if this row was 1? What do you guys think it will look like if this row is 1? Anyone? So what do you guys think this copula would look like if my row were 1? Would anyone want to draw here? I guess I can give you guys, so there is an option where I can allow you to annotate as well. I guess if you click on annotate, you can actually draw in the box that I have drawn here. Super cool. Would anyone want to try drawing it here? Oh, you guys can't see can you guys see a box that I have drawn here?
No, ma'am.
The internet. I just don't know what to do. Okay, forget about that. You guys can hear me, right? Well, we'll try that cool stuff sometime later. So this will just be a straight positive line, right? Because if we have a row of 1, we know it's perfectly correlated. Then you would have just a straight line. Gaussian copula. And in that case, you wouldn't even, care about measuring this. Can you guys see that I'm scrolling up and down? Yeah. So
Yes, ma'am.
okay, thank you very much. So again, remember if I have my row equals to 1, I will just have something which is like comonotonic. If I have my row is -1, it's going to look like counter monotonic, and if my row is 0, it's going to look like comonotonic, Gaussian copula. So sorry, if my row is 0, it's going to look like independent Gaussian copula. So I guess that's it about this Gaussian copula. Oh yeah, and I guess they have tried to define this bivariate Gaussian copula, but again, you see there are integrations which you haven't yet solved. So again, it is not mathematically possible to solve these equations, which is why we don't have a closed form solution to discuss. And again, so here what they're talking about is that this is just a bivariate case that we had a look at, right? Now, if you increase it to D, let's say if you increase it to D random variables, I'm hoping you guys can see what I'm drawing. Oh, this is not internet issue. This seems like Micro Studio issue. Wait. I see why this is happening. I guess now you guys can see what I'm writing.
Yes, ma'am.
Oh, okay. It was an internet issue at least. Okay, so what I was trying to say is that let us say if I have D random variables, okay, then now because I only had U and V, I can summarize their correlation with just one number, which is rho. But now if I have D random variables, I will instead have a matrix. So 1, 2, 3, let's say I am looking at 4. My D is 4. So I'll again have 1, 2, 3, 4 here. And I'll have something like this. So again, this matrix, so I'll have, again, this would always be 1. The diagonals would always be 1, right? Because the correlation between 1 and 1, 2 and 2, 3 and 3, 4 and 4 is again going to be always 1. And whatever you observe here will be what you observe here, because my correlation between 2 and 1 is same as 1 and 2. I mean, if my 1 increases and if my 2 also increases, then I know that if I increase my 2, my 1 is also going to increase. So my rho for U and V and U is going to be same. And so you will have a symmetric matrix here, which will define the correlation, all the correlations between the variables that you have. So remember, you only had 2 and you only need one number. So that is why you had a row. But now if you look at a D by D column, D by D matrix, which is what they're talking about here. So it is a D by D correlation matrix, which I just drew here. I mean, that will be what you will have along with the individual marginals, which will allow you to reproduce a joint distribution. And in this case, because you were looking at bivariate Gaussian, you will have a joint normal distribution. So I guess what we're trying to do is we have a value of U, we have a value of V, and we will have this correlation matrix, and we will know what distribution our individual marginals follow. And by using this correlation matrix and by using those U and V's structure, you will derive a joint structure for U and V, which will have embedded within it the same kind of dependency structure that was shown in the correlation matrix. And that is the power that copula has. And that is something that you can use to basically get to the joint distribution. Okay, so now I'm looking at students T copula, which is just another kind of copula, another kind of implicit copula, if I may. So here we have two parameters. One is gamma, other is rho. So rho is again going to measure, as usual, the correlation, but here gamma will represent the degrees of freedom. And again, whenever I'm talking about degrees of freedom, it will allow me to, have some variety here. So let's say if this were a Gaussian copula, then what would you see? You would see that you have a dependency, I mean, not exactly dependency, but here and here. So in the right bottom corner, and in the left upper corner, you had nothing going on, right? But if you're looking at T, you do see some points here, some points here. There is some chance, even if minutest, that you will observe a value of V which is lower, given that you have observed a value of U this high. And that is what happens in T. And again, if you see, these are a bit more denser than what it was in the Gaussian case. So it does kind of tries to capture this dependency a bit better than your Gaussian copula would. So I guess that is all they are trying to say here. And yeah, if your degrees of freedom extend to infinity, then yes, your T copula will tend to go to Gaussian. So it is similar to the case where you try to approximate your T distribution with copula. Oh, by the way, do you guys really think, I mean, when I was trying to study this about, when I was trying to study my T distribution, I saw that people often call it student's T copula. Would someone really name their child as student? What do you guys think happened there? Do you guys know the story of why is T named student? Have I told you guys that? Have I? Hello? Hello? Oh, am I audible?
No, ma'am. You're audible, but you haven't told.
Okay, all right. Just the fact that you answered me that I am not audible would actually, tell me that I am audible, because until you can hear my question, how can you answer it? But yeah, I guess, okay. So what happened with this guy was, I hope I'm remembering the correct name, but I guess it was something like GOSSET. So I don't know if T is silent or not, but let's just say that it was someone named William Gossett, who wasn't actually a statistician. He was in some another field, which again I have to forget now. But yeah, he was in some another field, and he wanted to publish a paper with this T distribution, not exactly copula, but the T distribution that we have. And what he tried to publish that paper under a pseudonym for people to take him serious, because he wasn't from statistics background. And that is where he chose the name of student, because he considered himself as a student and a lifelong learner. And yeah, so that is why we have students T, and it's just like there instead of his actual name. Its pseudonym got stuck, and now we call this students T distribution. And whenever we're looking at that kind of a distribution in copula, we say it's students T copula. But yeah, I think with every mathematician and statistician, there is so much of nice stories and histories and backgrounds. And sometimes it's depressing as well, because most of these extremely intelligent people do not, they meet their end and their fate is just sometimes not good, but then you just wonder what could have happened. You can never really, know what happens in the road that you haven't taken. So you just try to keep wondering what would have happened if not this and something else. But yeah, let's try to focus on the copula function. So now that we have studied, about copula, what it does and what it does not, we'll try to see how do we actually fit a copula. So sometimes what will happen is, you will have the data first. You will try to plot it, and you will try to see what kind of dependence is evident. And then you would want to measure the exact kind of dependency that there is, which is why you will use a certain kind of a copula. So let us say you observe that there is no dependency. So you would of course go for independence copula. And that will allow you to, basically forecast things in future once you know the actual number of that you will get as a value for the copula or dependency in the tail again. So we have to remember that we are trying to measure the tail dependency. And I guess what they have just done next is a tabular form. And I don't know why they have L raised to lambda here, but I guess it should be lambda and subscript L. So this is just the lower tail dependence and this is just the upper tail dependence. And if independence, it has to be 0, comonotonic 1. Counter monotonic is something like this, so no tail dependency, neither lower nor upper, so 0. And in Gumbel, no tail dependency, and this is what we derive. And in Kitten, if you sit and derive, you will get these answers. And for T, you will have these answers. Again, for varying rows and for varying gamma. And that is just to sum up. But again, I think what we can do is we can try to answer this, okay? So tell me what copula should I be using if I have all of these cases. So let us say I have independence. So if my data exhibit independence, what kind of copula should I be using? I guess it shouldn't even take this much of time.
Independent copy.
Exactly right. It will just be independent copula. So it will just be U times V, correct? And then if I see in my data, there is some higher upper tail dependency, but no lower tail dependency, then what kind of copula do you guys think will fit best here?
Gumbel.
Yes, exactly. It will be Gumbel, right? Okay, so next up, I guess we have a high degree of positive interdependence throughout. So you would kind of expect something like a comonotonic copula here, right? We have, at least in comonotonic, you have a perfect positive, but here they don't exactly say perfect positive, you have a high degree. So it could also be some copula which doesn't actually have a line, but something that is around that line. So you see that you might have some strong positive dependency going on in the frank copula. So what I drew, it was something like this, right, for frank copula. So I guess that also satisfies, at least according to the book it does. But I would say even if you write comonotonic, you should be fine. Okay, so the next one we have a high lower tail dependence, but no upper tail dependence. What was this?
Clayton.
Clayton, exactly. And then we have a high degree of negative interdependence throughout. So yes, counter monotonic. And I guess the answer would just be counter monotonic, right? I don't know why they have written frank. Oh yeah, I guess in frank, yeah. So if you look at your book, in frank copula, there is some sort of dots here and there as well in the negative. But yeah, I guess that's it. So there is not quite upper tail dependence, but there is a high load escalator. And now I guess we are having a look at this, right? A high degree of negative interdependence throughout. So I guess when we're saying a high degree of negative, I would say counter monotonic goes the best, but they have also mentioned frank. But again, I guess, yeah, that depends on the parameter that you have. So I guess that's it. But again, now if you're looking at no upper and lower tail dependence, that would again just to be, your independence copula or frank copula or Gaussian copula or counter monotonic copula. So yeah, counter monotonic copula would just be a case where your Gaussian copula has rho equal to -1. So you can write that as well. And the next case is where you have both kind of tail dependency, which will be captured by students' T copula. So I would say that was just a quick revision. And now we look at how do we fit a copula. So again, sometimes what happens is once you have the data, we know it's very easier for us to just substitute in the values and try to measure either the Pearson's correlation coefficient or the Spearman's or the Kendall's tau, right? And why bother with copula? So we now that we've already established how much important looking at copula is, we try to see whether there exists some sort of a relationship between the dependency of the whole data set and the tail dependency. So luckily there does exist relationship between these guys. And if let's say I were to write, so what will you do now is you will just find the value of your so again you won't go for Pearson's because it is not invariant, and you can only go for Spearman's or the Kendall's tau because they depend on the rank. and that rank will actually, render it being invariant to any monotonic transformation, increasing linear or nonlinear. So because of that, you would really, do something like this. So you would just take your data, you would try to figure out its Spearman's correlation coefficient, which is rho, or Kendall's tau, which will be tau, and then you will try to figure out the value of copula using that. Not exactly the value, but the parameter of the copula at least. So I think I should just maybe write it. I mean, it's just for you guys to know that if you, this is Kendall's tau. This is actually written as this in terms of copula. So again, you are taking D, C, U, comma, V, and you have a -1 here. And again, if you were to write rho, it will have something like, double integrals U, V, D, C, U, comma, V, -3. So this actually has a really cool interpretation, I would say. I mean, the area under the copula, the area under this double integration actually measures the volume of the copula that you're looking at. And I would say, we don't really have this, but there is a bound for these guys to even exist. But yeah, we can, at least for now, we can ignore this and we can go on and check the relationships that they have given to us. So what they are trying to say is that for the Gumbel copula, the Kendall's tau can be summarized as 1 - 1 upon alpha. So if you have data and if you try to figure out the value of this Kendall's tau, you can easily, figure out the value of alpha. So that is what they've done here. They've given you that Kendall's tau is 0.75, and then you use the method of moments to figure out the value of alpha, which is the only parameter in the Gumbel type copula. So once you know the parameter, you know E, log, and that's it. You know the value of the copula as well at the end. Once you know the value of U and V. So I guess that's it. And again, they have defined the Kendall's tau for Clayton copula, which is something like this. Oh, so one thing that you should remember is, because we're using method of moments, we are in a way estimating, right? So never forget this hat on the parameter that you add on here. Once you equate this to the estimated value of Kendall's tau. So I guess that hat is really important. And yeah, that's it. So anytime, I guess, if these sort of questions come in the exam, I guess this is fairly easy and straightforward to do. And I think a question like this is more likely to come. So this was not exactly precisely this, but somewhere around this was the question asked in the previous exam as well. But let us just see, I guess this is just a recall about what a copula is. Yes, it is a function. Yes, we know it's a function. And it takes the marginals of random variables as inputs and outputs a corresponding joint probability. Yeah, blah, blah, blah. Bivariate. Yes, so we do know all of this. Okay. So remember, when I'm writing copula xy, and yeah, it is also written in, this is just a compact form. But always remember, if you're writing f of x here, you should write u. If you're writing x, you write x there. So I guess that's it. And now let us try to solve this question, because this is a very interesting question and a fairly straightforward question if you have understood the concept of copula well. So who would like to read the question? Here, would you want to read the question for us? Up until here. Don't read this.
Let x is equal to a person's height measured in centimeters and y is equal to weight measured in kg. Heights and weights are each assumed to be normally distributed and their probabilities are given. Calculate the joint probability that a person's height is less than or equal to 180 centimeter and their weight is less than or equal to 70 kg using independence formula.
Yeah. So what do you guys think should I be doing here? First of all, should I define what is my u and what is my v here?
Yes, u is probability x less than equal to 180.
Exactly right. So we know for a fact that what is my u? U is just f of x. And what is my v? F of y. So if I consider that my height is x and my weight is, they have given it, height is x and weight is y. So what you will have here is this as f of x, I mean at least f of 180. So you get this value for u and you get this value for v, right? And now if you want to figure out the joint probability using an independent copula, what is my formula for independent copula? Just u times v. So it's just going to be multiplication of this guy and that guy. Easy, right? Okay. So now let us try to do the same thing using Gaussian copula with rho equals to 0. So even without doing any calculations, can you guys guess what should be the answer for this B guy here? So I'm looking at a Gaussian copula with rho equals to 0. How would you guys guess? Yes.
If rho is 0, it is again independent, right?
Exactly right. So it's, I mean, the Gaussian copula with rho equals to 0 is going to behave as if it is an independent copula. So we should ideally get the same answer. So let's check if that happens or not. So again, I mean, we have to derive. I mean, that is what we expect, but we also have to derive. And I think even if you write that, it should be fine. But what they next says, compare the two results in one. So then now if they're asking you to compare these guys, so you know that, you can't really write that Gaussian copula with rho is 0, it's just independent, so the answer is going to be same. Because the comparison has to be done here. So you will have to sit and derive the Gaussian copula with rho equals to 0. But one thing, do you guys know the formula of Gaussian copula? No, right? We only know it in terms of phi and its inverse, right? So let me just maybe go to the answers and we can see, I guess. Yeah. So if you have a look here, this is how my Gaussian copula looks like. Yes. Why have they written a perfect positive correlation? Okay, I don't know why they have written a perfect positive correlation, but we have a row of 0. Okay, there is no correlation. All right. So what we have to do is we have to measure the probability that these guys' height will be less than or equal to 180 and simultaneously its weight will also be less than or equal to 70. So you just substitute in the values of u and v correspondingly in the function that you have here. And using the tables, I think, so what is this? This is again standard normal. This is also standard normal. So you just get the values for these guys and these guys. And you know that, I mean, from the tables booklet, again, I have mentioned it, you will get this as 0.9 and this as 0.5. And now you have this thing. And now to figure out the value for this P here, they have given us a table here. So if you have a look at the 10th column here and the 6th column here, you see that the answer is 0.5642, which is exactly the same as you have here. So yeah, I guess let us see how they compare this. Yes, the result of both calculations are the same. This is because for multivariate Gaussian, a correlation coefficient of 0 implies independence. So I guess this question, I mean, so if you have a look at the last year's question for copula, I guess it was around for, I don't exactly remember, but I guess it was around 6 to 10 marks, somewhere between that. And it did ask something of similar nature. So it gave you some rows and you had to figure out the value of copulas for those different rows. And then there was some comparison to be done, I guess. Yeah, but it was something of a similar nature, I would say. So you guys shouldn't really expect heavily derivation induced questions. But yeah, I mean, something that would test your knowledge of these chapters is something that you should definitely expect. So I guess a question like this is really nice. And if you can solve this, then I guess you should be okay. And let me just have a look at the end chapter questions. So this summary, I guess, is really nice, once you sit and try to solve this chapter questions, you should just go through summary and then try to solve the questions. And then wherever you get stuck, you can refer to the class notes or the lectures. And yeah, I guess that's it. So there are some questions here that we can also go through. So I guess I can just maybe, discuss lightly. So what we have here is this. We want to figure out this Spearman's rule. So I think this is easy. You guys will just have to substitute in the formula and you get the answer. And here you have these two random variables which represent the future lifetime of two 40-year-old individuals and two lives of marriage. Okay, so whenever we are looking at such cases, we know copula would come handy, right? Because what happens is sometimes, even if let's say you are looking at the insurance case, there is a couple insurance that you can take out, right? So sometimes you never know if, let's say, what are the chances that if one spouse, let's say, dies, then what is the chance that the other spouse is also, dead. So, let's say they're traveling together and their car meets an accident or something, then the chance increases. So you will want to try to capture that. And I guess here what we are seeing is the joint probability that both lives will die by the age of 65. So that is what you have to figure out. And you're given the probability that x is less than or equal to 25 is so and so, and y is less than or equal to 25 is so and so. So now you have to use this Gumbel, copula, Clayton, and Frank. So I guess you guys already know the value of u and the value of v, and you guys know the value of alpha. And I guess it should be fairly straightforward at least. Do you guys want to try this question right now? I guess we do have some time left. Would you guys want to try this question now? At least try it with Gumbel copula. Forget about Clayton and Frank. It's just going to be the same thing again. Just try using Gumbel copula. And then we'll just see the second part of the question. So yeah, just try to do that. And again, remember, we are given that x is less than or equal to 25. But what we have to figure out the copula for is something around 65. So you will have to take into consideration that as well. Are you guys solving? Are you guys trying this question? Yes or no?
Yes, ma'am.
Yes.
Okay, yeah. Okay, yeah, good. So what are you guys doing now? I mean, we know that my probability that x will be less than or equal to 25 is something and y less than or equal to 25 is something. But they're asking me to figure out a joint probability that both lives will die by the age of 65. So in essence, what I'm asked to do is probability that x will be less than or equal to 65, comma, y will be less than or equal to 65, right? Is that what I have to figure out?
No, ma'am, it's the same thing because the age is 40, right?
Yeah, exactly right.
Yes, ma'am.
So again, remember x and y do not represent the lifetime. X and y represent the future lifetime, right? It represents future lifetime. So I guess you have to read question carefully. And now because they're saying that these guys are already 40-year-old, so what you care about is the 25 aage ka, right? Because 65 minus 40 is just 25. And you know the U and V for 25, so I guess now it's just Gada Majuri. So what you can do is you can skip that part at least in the class, but you guys should practice it. And what? Lower. Oh, this is not what we have to do, right? Oh yeah, this 17.7. Yeah. So again, we are just. I mean, you just have to substitute in instead of alpha 5, and for U and V, you will substitute in these values. So for Gumbel, you get 0.0986. For Clayton, you get something like this, and for Frank, you get something like this. I mean, this is fairly straightforward, I would say. So, but what matters is sometimes, so you get two marks, you get 6 marks right then and there. And now if you want to fetch more 3 marks, you will have to explain and comment. So again, now whenever I'm trying to, figure out that these both lives will die by the age of 25, what I'm looking at is x less than or equal to something, y less than or equal to something, right? And out of Clayton, Frank, and Gumbel, which copula do you think will best be able to predict this? Anyone? Okay, first question, what kind of dependency are we looking at? Are we looking at the lower tail dependency or are we looking at the upper tail dependency? What do you guys think? Yes. What do you guys think are we looking at?
Lower tail dependency, ma'am, right? Because we are calculating x less than equal to 25 and y less than.
Exactly right. So because we are looking at less than, it's measuring lower tail dependency. And now what kind of copula amongst these three will measure lower tail dependency the best? Look at the graphs that we drew.
Clayton copula.
Clayton.
Exactly right. It's Clayton. So if you have a look at these probabilities and check which one has the maximum, it will be Clayton, right? 0.1, 0.05, and 0.09 here. So Clayton copula has the highest probability amongst these three. So again, that is what they have commented here as well. The Clayton copula gives the highest probability. Blah, blah, blah. This is because it exhibits lower tail dependency, right? And exactly, I mean, that is the thing that you would want to capture here. So they're talking about some broken heart syndrome here, which you need not mention. They do not expect you to know such medical terms. I don't know if it is a medical term or a psychological term, but yeah, it looks. But yeah, you just have to mention that because there is quite a chance. I mean, let us say even if there's an earthquake, and if both of them are in a house and they are married and they are in the same house, then there is a chance that if one person dies, there's a very high probability that the other person would be dead as well, if they're at least in the same house. So that is how you can, that somehow you should use a copula which has a higher degree of positive interdependency. I mean, if something happens to one guy, that same thing is going to happen to the other guy as well. So that is why they are saying that you should look at the common atomic copula, and among the three copulas that you have here, Clayton is the best one for this purpose. So any doubt with this? And again, whenever you are asked to comment, do comment on what works, but also comment on why the other thing does not work. So that is also very important to mention. And yeah, I guess just try to write things, because that would fetch you good marks. And what matters is not how much you write, but what is the quality of the answer that you write. So don't think, let's say this is like for 4 marks, I have to write like a page or something. No, you don't have to do that. So, okay, now do we have still, yes, we still have time left. So again, yeah, I guess derive the coefficient of lower tail dependence for Gumbel copula in the case where parameter alpha is 0. I guess these questions now you guys are, you guys know enough to solve these questions, right? So for the Clayton copula, again, determine the inverse generator function. So yeah, this is what I was talking about, right? So they have given you the generator function for Clayton and Frank copula. So you would just have to substitute in the 1 and 0 and see whether these are valid or not, and check if these are increasing or decreasing or what. So here you can clearly see that log of anything is going to take, log of anything is going to be a decreasing function, sorry, an increasing function. If you take a minus of this log, it's going to be a decreasing function. And then you have to just determine its inverse and then derive the copula function basically. So I guess that's easy. And here you want to just determine the coefficient of lower and upper tail. So I would say, if possible, do this by today or tomorrow, so that if you have any doubts, you can ask me. And I mean, it's fine if you do it later on. You can still ask me doubt, not that. But I guess now that it's really fresh in your mind, I think it's good if it fits right now itself, because there is going to come one question for minimum 5 and maximum 10 marks from this copula chapter for sure. And you see how easy it is, right? I mean, you don't have, these questions won't be really tricky. At least not if your concepts are very clear. So I guess, what are these? I guess these are just theory questions. So yeah, I guess that's it. So yeah, that is all from my side for today. Any doubts, anyone? Yes. Any doubts? Anyone want to do? You would want to ask anything? Why are you guys so silent? Are you guys there?
Yes, ma'am.
Okay. Yeah, at least say yes or no so that I know if you guys are here or not. Okay, yes, that's fine. So, okay, just to tell you guys, in next week, I'll be starting off with chapter number 1, okay? So, I guess the next, at least 1 month is going to be a very intuitive. So, up until now, the chapters that we studied, it wasn't, I mean, these are practical chapters. I mean, Copula is one of the heavily used tools in terms of risk management. And this is, I mean, we haven't even covered 1/8 of what Copula is. But I guess for anyone who would want to, go further in and do some future studies in finance or in risk management or in insurance sector at least, Copula is very, very heavily used. And what was the saying? Yeah, I guess that is what I was saying. No, yeah. So I was saying that, yeah, these aren't really quite, I mean, you can't readily, as of now, with the background that we have, see its application evidently. But the things that we'll be studying from now on are very, very much applicable. And it's so intuitive. I mean, you will feel as if we are just, talking through the solution and as if we are just having fun, basically, much more fun than now at least, if I may say that. So yeah, I guess that's all from my side for today. Do you guys want to ask anything?
No, ma'am. Thank you.
No, ma'am.
Thank you very much.
Thank you, ma'am.
Thank you very much. Enjoy the weekend, guys. This weekend I'm not gonna take any lectures, so you got it all for yourself.
Thank you.